Alright, welcome back. This is section 4.4, Polynomial Functions, Roots, and Irreducibility. So in this section, we'll be looking at polynomial rings of the type R adjoined X and F adjoined X, where R will be given as a commutative ring, not just a ring, but a commutative ring. So A times B equals B times A in the ring of R. And of course, F will be known as a field. So we're looking at polynomial rings where the coefficients come from a commutative ring, or polynomial rings where the coefficients come from a field. As we look at R of X and F of X as polynomial rings with elements f of X equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a1 x plus a0, where all the AIs are elements of the ring or a field if so designated. Now let us look at the elements as polynomials, which is the functions of X. Now, so we're switching this thing out. We've before been looking at these guys as the elements of these particular rings, and that's accurate. These are the elements of these rings. You know, when F adjoined X, when you got coefficients come from a field adjoined X, that makes an integral domain. If you've got an integral domain adjoined X, that's still an integral domain. But once you get commutative rings with identities adjoined X, they will not be integral domains or anything. They will end up being commutative ring with identities themselves. So it really depends on the ring that you're attaching to the X. But polynomial rings never become fields themselves. They are going to become either integral domains or a commutative ring with identities. Now, we're looking now as these are actually functions of X. That's what this chapter is all about. We're going to be looking at that idea of irreducibility that we talked about in the last chapter. So, definition. Let R be a commutative ring, and let f of X be an element of R joined X. An element A inside of R, the ring, is said to be a root or 0 of the polynomial if f of A is equal to 0 in R. That is, if the induced function f going from R to R maps A to actually 0 in R. This is the same definition that we talked about in junior high school and the like. Root 0 x-intercept, if you can graph these guys, is where the function is actually equal to 0. But since we're talking about the coefficients coming from rings in R, and R is a commutative ring, so rings adjoined X. So these are going to be polynomials, but when we plug in the number A into the polynomial replacing X, and I get 0, that makes A a root, also known as a 0. So, an example here is that f of X equals x squared minus 3x plus 2. And this is a polynomial in the reals adjoined X. The coefficients are come from the reals. So when f of X, which is equal to x squared minus 3x plus 2 equals 0, this thing's going to factor into x minus 1 times x minus 2. You set each factor equal to 0. X minus 1 equals 0. X equals 1. X minus 2 equals 0. X equals 2. So I get two roots. So x equals 1 and x equals 2 are roots of f of X, aka also known as zeros. So it depends on which textbook you use, whether they call them roots or zeros, but it's the same thing. Now that was with the reals adjoined X, but look at this next example. I got a polynomial g of x equals x squared plus 1. Again, element of the reals adjoined X. So the polynomial rings where the coefficients are real numbers. Then g of x has no roots in R. This thing cannot be factored. This would be an irreducible polynomial because there's no way to factor this guy. It can't be broken down into polynomials of smaller degree. Smaller than 2 would be a degree 1 times degree 1. However, if you change the world of where the field you're playing with, instead of the reals, let's talk about the complexes. So if g of x is equal to x squared plus 1, then g of x has two roots, also known as zeros, the I and negative I. And just to remind you, x squared plus 1 equals 0, means that, subtract 1 from both sides, x squared equals 1. You take the square root of both sides, plus or minus. The plus or minus the square root of -1 ends up being plus or minus I. That's where I get my two roots out. They're complex roots, but this thing actually has roots in because the field was the complex numbers. But if you just focus on real numbers, this polynomial x squared plus 1 is irreducible. So that's going to be kind of my game plan here in terms of deciding when a function is going to be irreducible versus when a function is going to be reducible. We're going to be looking for the zeros, the roots of a polynomial. So, Theorem 4.15 says this. Let f be a field. F of x is an element of f adjoined x, and a is an element of the field. Then the remainder, when f of x is divided by the polynomial x minus a, is f of a. Now this may look like something that is a brand new theorem, 4.15 out of our textbook. But no, this is a theorem that you've actually seen before. So I went out and grabbed myself an old pre-calculus college algebra textbook here, and I went up and looked at the chapter in terms of polynomials. And so I was going to pull in an old high school algebra book here, and it's called the Remainder Theorem here, as well as it's called the Remainder Theorem in our book. If a polynomial p of x is divided by x minus k, the remainder is equal to p of k. So when you divide by the linear factor x minus k, the remainder you get with that will be equal to the same thing as p evaluated at that k value. That is called the Remainder Theorem. And Theorem 4.15 in our modern algebra book is called the Remainder Theorem. It's the same theorem. So, again, what we're going to be looking for are zeros. But the first thing we need to know is about the Remainder Theorem. So, I put an example up here for you guys, just so let you know. Let's let f of x be equal to 3x cubed plus x minus 2, element of the polynomial ring, the reals adjoined x. And let's let g of x be equal to x plus 3. Let's see what happens here. When I take x plus 3 and divide it into 3x cubed plus 0x squared, because there's a term missing, plus x minus 2, let's see what kind of remainder I get. Well, what times x is 3x cubed? That would be 3x squared. And then I'm going to distribute. 3x squared times x is going to be 3x cubed. 3x squared times 3 will be plus 9x squared. And then after you multiply, you end up subtracting. And I subtract, which changes my signs. First term cancels. 0x squared minus 9x squared is a negative 9x squared. Bring down your next victim. Plus x. And play the game all over again. What times x is going to be negative 9x squared? Well, that would be negative 9x. Negative 9x times x would be negative 9x squared. Negative 9x times 3 would be a negative 27x. Now I want to subtract, which would change my signs. So this becomes a plus, this becomes a plus. This term will cancel. So I got x plus 27x makes it 28x. Bring down my next victim, minus 2, and play the game all over again. What times x is 28x? Plus 28. 28 times x is 28x. And 28 times 3 is 84. That would be plus 84. And then I'm going to subtract, which changes my signs. First term will always cancel. Minus 2 minus 84 will be a minus 86. The remainder is negative 86. Now, just to save some time, I decided to go ahead and write this one up for you. Now, with x plus 3, that was the factor that we divided into the polynomial, when you solve it for x, you get your k value. So subtract 3, k is equal to negative 3. When I plug in negative 3 into my function, remember f of x was equal to 3x cubed plus x minus 2. So f of negative 3 would be 3 times negative 2 cubed plus negative 3 minus 2. Negative 3 cubed is negative 27 times 3 is negative 81. Minus 3 minus 2 ends up being equal to, you got it, 86. Because that's what the remainder theorem told us. I could use that long division type thing here, or I could just plug it into the actual function, and that will actually give me the exact same value. When you divide by x minus c, or take c and plug into the function, you'll end up getting the exact same value. That's called the remainder theorem. The factor theorem. Theorem 4.16. Let f be a field and f of x be an element of f adjoined x, and let a be an element of your field f. Then a is a root / 0 of a polynomial if and only if x minus a is a factor of f of x. This also implies, by the remainder theorem, when I plug in f of a, I should get 0 in your field, so whatever that 0 represents. So, and again, talking about stuff you've seen before, this is stuff we did in junior high school and high school. So if I flip the page from the remainder theorem, you will see very distinctly, it comes in the next page here, slide it up, and again out of our old high school algebra book here, the factor theorem. The factor theorem actually states that a polynomial p of x has a factor of x minus k if and only if p of k is equal to 0. Compare that, and the way we wrote it up in high school, to the theorem 4.16, and you'll see it is exactly the same thing. That, quote, we talk about arbitrary things like being a field and the like, but still, let f be a field and let f of x be an element of f adjoined x, and a is an element of the field f. Then a is a root, 0, of a polynomial f of x if and only if x minus a is a factor. And again, according to the remainder theorem, that if f minus a is a factor, that means the remainder is equal to 0, so f of a would be equal to 0. So let's talk about this. I want to remind you of a few things from, again, high school math. So, give you another one. F of x is equal to 2x cubed minus 3x minus 10. And let us look at the linear polynomial x minus 2. Now, I'm going to do this problem 3 different ways to see what's going on here. I'm going to do long division because you need to practice that. Your long division, your divisor is x minus 2. Your polynomial is 2x cubed. There is no x squared term, so it'll be plus 0x minus 0x squared, that is, minus 3x minus 10. Now, in this example, I should have told you that this one, the field is going to be the rationals adjoined x. So, integer divided by integers, that's a field. The rationals are a field. So, my numbers have to come from rationals. Okay? Those are my field elements. So, let's do the long division. What times x is 2x cubed? That would be 2x squared. So I'm going to distribute. That gives me 2x cubed minus 2x squared times 2 will be a minus 4x squared. And then my long division skills, I would subtract, which changes my sign. So that's equal to, let's see here, 2x cubed minus 2x cubed. First term should always cancel. Otherwise you screwed it up. Plus 0x squared plus 4x squared is 4x squared. Bring down your next victim. Minus 3x. Y times x is 4x squared would be plus 4x. 4x times x is 4x squared. 4x times minus 2 would be minus 8x. Subtract, which changes your signs. First term once again cancels. And minus 3x plus 8x is a positive 5x. Bring down your next victim. Minus 10. Now what times x is 5x. That would be plus 5. 5 times x is 5x. 5 times minus 2 is minus 10. Subtract, changes my signs. First term cancels. And you got minus 10 plus 10, which you get the remainder is 0. From the long division, I can tell you that this polynomial f of x is going to factor into x minus 2 times that 2x squared plus 4x plus 5. Plus 0 remainder from the division algorithm, but since the remainder is 0, that gives you factors. So this is a reducible polynomial. Now that was kind of painful and long in terms of that division, but you need to know that because that's how you divide polynomial by polynomial. However, there is an easier method if you remember that when you divide by a linear term, a polynomial by a linear term, x minus c, you can also do what we call synthetic division. So synthetic division, you're going to take f of x and you're going to divide, use old term notation here, divide by x minus c. Then you're going to take c and divide into the coefficients of f of x. And if there's a term missing, you've got to put 0 in for it. So, just to remind you, because this will save us a lot more time here, if I've got the factor x minus 2, that will imply that the c is equal to 2. X minus c, so c would be equal to 2. So I'm going to take 2 and divide into the coefficients of my polynomial. It starts off with a 2x cubed. The coefficient is a 2. There is no x squared term, so you have to put a 0 in for it. Represents there's no x squared term. The x term is going to be a minus 3, and then the constant term will be a minus 10. The coefficients of my polynomial. Now, skip a line, draw a line, synthetic division. You bring down your first number, 2, and below the line you multiply, above the line you add. So 2 times 2 is 4. 0 plus 4 is 4. 2 times 4 is 8. Negative 3 plus 8 is 5. 2 times 5 is 10. Negative 10 plus 10 is 0. And you block off the last number because that's going to be your remainder. And if you look at your quotient down here, this 2 in the synthetic division represents the x minus 2. And look at your coefficients down here. This is your constant x squared. You're left with 2x squared plus 4x plus 5. And that happens to be exactly what you got up here. And it took a lot less work. And most important, you've got that remainder of 0. But if you're looking for if it's going to be a 0 or not, instead of doing the synthetic division and guess and check type method, you can just plug in what you think the 0 is into your polynomial, and if you get 0 out of it, you won. It is a 0. If you don't get 0, it's not a 0. So again, my function, just to remind you, was 2x cubed minus 3x minus 10. When I plug in 2, f of 2 would be 2 times 2 cubed minus 3 times 2 minus 10. 2 cubed is 8 times 2 is 16, minus 2 times 3 is 6, minus 10. 16 minus 6 is 10, minus 10 is, 0. So when you get a 0, this means that x equals 2 is going to be a root or 0 of your polynomial. So you got 3 different methods. But for us, synthetic division on the long division is a great way that we're going to check, because we are talking about linear terms that you're going to be dividing by, looking for those factors. Corollary 4.17 says this: let f be a field, and f of x is a non-zero polynomial and f adjoined x of degree n, then f of x has at most n roots in f. And that's an old high school math concept here. So if I'm dealing with a polynomial f of x, the maximum number of zeros, roots, x-intercepts I'm going to have on that polynomial is the degree of that polynomial. So f of x will be at most, that means less than or equal to n roots, and that n was the highest power, so there's a connection there. Corollary 4.18 says this: let f be a field, and f of x, element of f adjoined x, with degree of f of x greater than or equal to 2. If f of x is irreducible in f adjoined x, then it has no roots in f. So you're going to have pretty much degree greater than or equal to 2, and if f of x is going to be irreducible, it'll have no roots. So there is the connection between irreducibility and the concept of roots. If it's irreducible, it has no roots. That's going to be key. However, the converse of corollary 4.8 is false. Now the converse, remember the theorem says this, corollary: if f is a field and f of x is an element of f adjoined x with degree greater than or equal to 2, if f is irreducible, then it has no roots. You got to have all these conditions first. But going back the other way, it's not the case. So let me give you an example. F of x is equal to x to the fourth plus 2x squared plus 1. This thing factors into x squared plus 1 times x squared plus 1 in Q adjoint x. So we're talking about rationals here being the field. And f of x has no roots / zeros in Q, because if you look at this guy, this has a root of plus or minus I, this has a root of plus or minus I. So the i's are not in the rational, so these guys are not going to factor anymore, but the whole thing factored. That's because my degree was greater than actual 3. Once you get 4 or beyond, you can actually have some factors that won't show up as zeros. But f of x is reducible because as long as you can factor it, it's going to be reducible. So this guy, x to the fourth plus 2x squared plus 1, is actually a reducible polynomial in Q adjoint x. And notice that, again, f of x in our example has no roots or zeros in the rationals. But f of x is reducible in Q adjoint x because we could factor the thing out even though it has no roots on the guy. Again, the trick on that one is greater than or 4 degree is 4 or more is going to give you the problem. Corollary 4.19 says this: let f be a field, and let f of x be an element of f adjoined x, be a polynomial of degree 2 or 3. So we're looking at this particular scenario. Degree 2 or 3, not degree 4, not degree 1, but degree 2 or 3. Then f of x is irreducible if and only if f of x has no roots / zeros in f. So now we're talking about that real connection between irreducibility and looking for these zeros. So if I got a polynomial that is greater than or equal, well, basically degree 2 or degree 3, degree 2 or degree 3, and degree 4, we just get an example of that one. I don't want that. So it's either degree 2 or degree 3. Then f of x is going to be irreducible if and only if it has no roots or zeros. So degree 2, degree 3, it reduces when you actually have a 0. And a 0 is also known as a root, also known as an x-intercept. So our calculators are going to be very advantageous when it comes to these things. You'll see that later. Now, let's talk about this f adjoined x and talking about fields here. We're going to break fields into two camps, two different kinds of fields. Remember, there's two different kinds of fields. There's going to be a finite field and an infinite field. An infinite field has an infinite number of elements. You know, things like the reals, the complex numbers, the rationals. These have an infinite number of elements in them. Versus a finite field. That is a field that there's only a finite number of elements in it. That would be things like Z7, Z13, ... Z mod P. As long as you're modding out by a prime in your arithmetic properties of modulos, modular arithmetic, Z mod P, Z mod a prime will always be a field. You mod out by a prime, you always get a field in the wonderful world of modular arithmetic there. So, corollary 4.20 says this. Let f be a field, but not just any field. We want it to be an infinite field. And let f of x and g of x be an element of f adjoint x. Then f of x and g of x induce the same function from f to f if and only if f of x is equal to g of x in f adjoint x. So we're talking about, in the wonderful world of infinite fields, if you got coefficients can be from an infinite amount of numbers there, because of this infinite field type thing here, then basically what we're saying here is f and g induce the same function, which would mean going from f to f as a mapping, which is the same thing as f of x is equal to g of x. This does not work if your field is finite, because if you got a finite field, some of those coefficients could boom up or boom down and look like a different function, but they will actually act the same. This one says they will actually not just act the same, they will be the same. So, here comes the big deal about this stuff. What can we do with the information we discovered from Chapter 4 in general? So from Chapter 4 in general, we can go back, and I'm talking about not just Chapter 4.4 material, which I'm going to get to with some examples there, but I'm also going to go back and look at examples from Section 4.1 and 4.2. And one of them, just to remind you, is the GCD. So let's work at this particular problem. It says find the GCD of 2x to the fourth plus 5x cubed minus 5x minus 2 and the polynomial 2x cubed minus 3x squared minus 2x in Q adjoint x. So we can have fractions as coefficients, but that's the worst it's going to get, adjoint x. Now what we're going to be using here is, of course, we're going to use the division algorithm. Remind ourselves of what the division algorithm is. Well, I'm going to sit there and do long division on this guy because I'm dividing by something that is bigger than x minus constant type thing here. So I got two polynomials. I'm going to divide them. Well, if I'm going to divide them, I want my dividend to be the largest degree polynomial and my one that I'm dividing by being the smaller degree. So I'm dividing by the smaller degree, which would be the 2x cubed minus 3x squared minus 2x. I'm dividing it into the polynomial 2x to the fourth plus 5x cubed minus 5x minus 2. So let's play the long division game, of which you do have no choice on this one. What times 2x cubed is 2x to the fourth? That'll be just x. I'm going to distribute. That gives me 2x cubed times x is 2x to the fourth minus 2x squared times x is minus 3x cubed. X times a minus 2x will be a minus 2x squared. But you'll also notice in this problem, I've got a term missing. There's no squared term, so I need to put that in there. That'll be plus 0x squared minus 5x and then minus 2. You always have to put your zeros in there so things are going to line up. Now it lines up there. And then once you multiply, you distribute, you subtract, change your signs and distribute there. So it becomes a minus, that becomes a plus, this becomes a plus. And the first term should always cancel. 2x to the fourth minus 2x to the fourth. Plus, I got 5x cubed plus 3x cubed. I can do that kind of math. That's 8x cubed. And then I've got plus 0x squared plus 2x squared is plus 2x squared. And then I bring down my next victim, minus 5x. And I play the game all over again. Now, what times 2x cubed is 8x cubed plus 4. 4 times 2x cubed is 8x cubed. What is 4 times negative 3x squared would be minus 12x squared. And 4 times a negative 2x would make it a negative 8x. Then I'm going to subtract, which changes my signs. First term should always cancel. I'm left with 2x squared plus a 12x squared makes it a 14x squared. And I've got a minus 5x plus an 8x. That would leave me with a plus 3x. And then I got the minus 2 being pulled down. Since 2x cubed doesn't go into 14x squared because your remainder polynomial is a degree less than what you started with, you can't divide anymore. So what I've got here is the x plus 4 is my quotient. There's my big polynomial I started with, which is the dividend, and what I'm dividing by is the divisor, and the guy on the bottom is the remainder. So if I write this division in terms of the division algorithm, what I'm going to have here is this. The big polynomial, which is 2x to the fourth plus 5x cubed minus 5x minus 2, is actually equal to the divisor, which is 2x cubed minus 3x squared minus 2x, times the quotient, which is x plus 4, plus the remainder, plus, and this would be your quote 14x squared plus 3x minus 2, squeezing it in there. Okay? Now, remember your division algorithm. You're going to do this shift A. So your divisor becomes the dividend. This is 2x cubed minus 3x squared minus 2x. That will be equal to, your remainder becomes your divisor, 14x squared plus 3x minus 2, and then you got to go find a new quotient plus a new remainder. So now we're going to come over here and do some more long division. I'm trying to do my long division on the left side of my paper over here so you guys can see this. Alright, now the big polynomial is my divisor, which is the 2x cubed minus 3x squared minus 2x plus 0. If you got a term missing, put a 0 in for it. Divided by 14x squared plus 3x minus 2. The remainder from the one division turns into the quotient of the next division as you're doing the shift method. And remember, you're looking for the GCD. The GCD is going to be this remainder before the remainder of 0. And don't forget, GCDs have got to be monic. Remember that in the back of your head. So let's play this game. But now look at my numbers. 14x squared times what is equal to 2x squared, 2x cubed. Well, this is when, you know, obviously fractions are coming in half. To turn a 14 into a 2, I've got to divide by 7. So this will be 1/7. What times x squared is x cubed will be x. Now I'm going to multiply and distribute. 1/7 x times 14x squared, that makes it 2x cubed. Then we get crappy fractions here. 1/7 x times 3x makes it plus 3/7 x squared. And 1/7 x times a minus 2 makes it a minus 2/7 x. Now I'm going to subtract and change my signs. This will be a minus, this will be a minus, this is a plus. First term should always cancel. And I've got here negative 3x squared minus 3/7 x squared. So combine like terms, that makes it 3 over 1, and then multiply by your common denominator, which is 7. That'll be negative 21 over 7 minus 3 over 7. Makes it obviously minus a 24 over 7 x squared term. Now minus 2x plus 2/7 x ends up giving you a minus 12/7 x. And then bring down my last victim plus 0. Now, here we play the game again. What times 14x squared is negative 24/7 x squared? Well, to figure out what you need to multiply by, you should be able to figure out the variable very easily, but the constant, you take your constant here, which will be your negative 24/7 and divide by 14. And when you do that, you get an awful fraction of negative 12/49. So when I distribute this guy, negative 12/49 times 14, you end up getting, that was kind of the purpose of it, a negative 24/7x squared. A negative 12/49 times a negative 3x gives you a negative 36/49 x squared. I'm sorry, x. X squared was this guy, x. And negative 12/49 times a minus 2 becomes a plus, and that's going to be a 24/49. Now I'm going to subtract, which changes my sign, so this now becomes plus, this one becomes plus, this one becomes minus, and the first term will cancel. Negative 12x plus 36/49 x ends up giving me a negative 48/49 x, breaking like terms there, and then 0 minus 24/49 is minus 24/49. And since 14x squared doesn't go into your x term, this guy is my remainder. So by this information, I know the remainder part is going to be that awful fraction of negative 48/49 minus 24/49, and my quotient was 1/7 x minus 12/49. So I now have my division algorithmic method of finding the GCDs. So once again, I'm going to shift. Okay, so when I shift, this gives me 14x squared plus 3x minus 2. That'll be equal to, again, your divisor becomes the dividend and the remainder becomes the divisor. That's equal to negative 48/49 x minus 24/49 times somebody plus remainder. So one more long division here. So here we go. I'll slide this up and put my long division here. My divisor is this awesome rational polynomial here. Negative 48/49x minus 24/49. My dividend is 14x squared plus 3x minus 2. So now I'm going to start cheating with the old calculator just to show you how I got this thing here. What times negative 48/49 is equal to 14? Well, pretty much you take 14 and divide by parentheses, that negative 48 divided by 49. And crappy fraction, and convert the crappy fraction into negative 343/24. Gotta love it. So this will be negative 343/24 times x, because the x times x equals the x squared. Now I'm going to distribute and multiply, but we just discovered negative 343/24 x times negative 48/49 x. Negative times negative is a positive, and it ends up giving you a positive 14 x squared. And now the negative 343/24 times x times a negative 24/49 ends up giving you 7. That's nice. That becomes plus 7x. Now I'm going to subtract, which will change my signs. This becomes a minus, this becomes a minus. First term cancels. I've got plus 3x minus 7x makes it a negative 4x. Bring down my next victim, minus 2. And what times negative 48 over 49x equals negative 4x? We'll just take the negative 4. I'll show you, I'm doing this actually on the calculator here. I'm going to take the negative 4, and I'm going to divide by parentheses what I'm trying to multiply by, the negative 48 divided by 49. And the answer is 4.083333, so I'm going to go with the classic fraction on that one, which makes it 49/12. So this will be a plus 49/12, so when I distribute negative 48 over 49 times 49/12, the 49's cancel. Negative 48 divided by negative 12 equals a negative 4. That'll be a negative 4x. And negative, watch this one, 48 over 12 times negative 24 over 49 over 12 times a negative 28 over 49. The 49's cancel. 12 goes into 24 two times, and positive times negative is a negative. And I'm going to subtract, which changes my signs, and the first term cancels, but in this case the second term also does. And finally, I got a remainder of 0. So, your division algorithm here, your negative 48 over 49x minus 24 over 49 is multiplied by negative 343 over 24x plus 49 over 12 plus the remainder of 0 there. And remember, to find the GCD, the GCD is the remainder before the remainder of 0. And that remainder was, a little squiggle equal to, that negative 48 over 49x minus 24 over 49. It's the remainder before the remainder of 0. But there's a problem. This is actually the wrong answer. Why? GCDs must be monic. What is monic? A monic polynomial is a polynomial with a leading coefficient 1. So this isn't my answer. It's an associate to the answer. So what you do to make it monic is you've got your negative 48 over 49 times x minus 24 over 49, and you multiply by the reciprocal of the leading coefficient, which would be a negative 49 over 48. And I'm going to distribute to make him monic. So the monic part of this guy would end up being negative times negative is positive. Here, these guys completely cancel, so you're left with just 1x. That was kind of the purpose. Now over here, the negative times negative ends up being positive. Here the 48's cancel, but the 24 goes into 48 a half time. 2 on the bottom, if you will. So there's my equivalent associate to actually the remainder I got with the division algorithm, but to make him monic, that makes the GCD x plus 1/2. So therefore, boom, 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 the GCD of 2x to the fourth plus 5x cubed minus 5x minus 2, and the polynomial 2x cubed minus 3x squared minus 2x is equal to x plus 1/2. There is my GCD. And honestly, most people will screw this up, and it's impressive you can get through the interesting algebra, especially with the fractions on this thing, of the long division without making a careless error. But how many times have I had students circle this answer and they forgot to make the polynomial leading coefficient has to be 1 to identify it as an actual GCD. That's why the two polynomials are actually associates. Now another example that we're going to be playing around with is the idea of factoring a polynomial as a product of irreducible polynomials. We want to rewrite any polynomial as a product of irreducible polynomials. So, this time, to make it easier on you guys, Yeah, because I've given you a finite field. Now, if I gave you an infinite field, for example, this example I gave you Z7 adjoined X. But if I gave you like the rationals or whatever, that's when you're going to be graphing the polynomial, looking for it crosses the x-axis, doing all the tricks that you had in the past. But on this particular one, when you have a finite field, it's going to be a little bit better. So, in this problem, we got Z mod 7 adjoined X. So my coefficients of my polynomial are the equivalence classes 0 through 6. Now I wrote the polynomial like this because the book does. It is 2x cubed plus x plus 3. Now I could have written it like this. F of x is equal to equivalence class 2 times x cubed plus equivalence class 1 times x plus equivalence class 3. Then that would be correct in Z7, and that's officially Z7 adjoined X. That's where your polynomial ring is coming from here. However, it's a bunch of pain to write these little pointed brackets. So traditional notation, we just write it like this, but we're letting you know that these are polynomial rings in Z7 adjoined X. And it's got to be a field, and to be a field, you've got to mod out by a prime number. Now, here comes the idea, and it's called the factor in combination with the remainder theorem. So here's the deal. Here's my polynomial. To be able to do this particular polynomial, I want to be able to factor it. I got to find zeros. Now, I can sit there and kind of graph this thing or whatever, but this is an unusual world. It's not like it's the reals. So reals are complexes. They'll show up on your graphing calculator in the graph mode. That's not where we're at here. We're in Z7 adjoint X. So the trick is this. In Z7, which is my field where the coefficients come from, we're only allowed to have the elements 0, 1, 2, 3, 4, 5, and 6. That's why I chose Z7. It was big enough to actually give you a lot, but not big enough to hurt you. Those are the actual elements of just Z7. And I'm looking for zeros. And according to the zero and factor theorem, to get the remainder of these guys, when I divide, all I've got to do is plug these numbers into my function. That's going to save me a lot of time. Here's my polynomial. 2x cubed plus x plus 3. So I'm going to come over here and turn on my calculator, show you another trick, and there's two tricks I can show you on this one. I'm going to go to y equals first and type in 2x cubed plus x plus 3. Okay? And the first trick is I'm just going to do a zoom standard, negative 10 by 10 screen. And I know there's the graph of it, but I'm not looking for zeros to actually cross the x-axis because I'm in Z7 adjoint X. All I'm going to do is evaluate this function at these points. Second, calculate value. What's the value of the function when x equals 0? Yeah, it's 3. I could have done that without much math there, help. But now the rest of them, when I plug in 1, I end up getting 6. When I plug in 2, I end up getting 21. When I plug in 3, I end up getting 60. When I plug in 4, I end up getting 135. When I plug in 5, I end up getting 258. And when I plug in 6, I end up getting 441. Well, I don't see any zeros, Dr. Taylor. Well, yeah, you don't. Not at this point, because we're in Z7, and some of these numbers are bigger than Z7. So I can take these numbers and see what they are in the world of Z7. And again, we're going to look at these guys as part of that. Got to be numbers in Z7, but it is a polynomial where it's coming from adjoint X. So 3 is pretty much 3 because that's in one of my equivalence classes. 6 is 6 because that's in my equivalence class from 0 through 6. 21, well, I can either divide by 7 or just take 21 and subtract a couple of 7s out of it, and I end up getting another 7, And if you notice, 21, when it's divided by 7, you end up getting 0. 21 divided by 7 is 3 with no remainder. So I just found my first 0. 60 divided by 7 leaves me with a remainder of 4. Or I could have taken just 60 and keep subtracting all multiples of 7 until I get between 0 and 6. 135, when they start getting big, show you some more tricks in the calculator. 135, I pretty much divide by 7 and see what the remainder is. I don't care about the whole number part, get rid of the 19. There's my decimal, and if I convert that to a fraction in terms of base 7, it's 2/7, so 135 is equivalent to the numerator of 2. 258 divided by 7 doesn't go into it evenly. So I'm going to subtract off the whole part, 36, and then I just convert that decimal into a fraction and I get 6/7, and the remainder is always the numerator out of 6 out of 7. And the last one is 441. I'm going to divide that one by 7, and you notice I end up getting 63. It goes into it evenly with no remainders. So I happen to have 2 of these guys being zeros. So what I'm going to do here is, to be able to reduce this polynomial, I'm going to use this synthetic division. So, remember, C is going to be a 0. That also means that x minus c is going to be the factor. But my 0 is going to be 2. So I'm going to take 2 and divide it into the coefficients of my polynomial. And if there's a term missing, don't forget to put 0 in for them. So this would be 2x cubed plus 0x squared plus 1x plus 3. Constant x squared, x cubed. Skip a line, draw a line, and I should get a remainder of 0. So bring down the 2, you multiply 2 times 2 is 4, you add, you get 4. 2 times 4 is 8, you add, you get 9. 2 times 9 is 18, add, you get 18, and 3 plus 18 is 21. Well, I didn't get 0. Yeah, but you remember these numbers go beyond Z7, so I got to put it back in the wonderful world of Z7 to join X. 2 is good, 4 is good, but in Z7, 9 is equivalent to 2, and 21 is equivalent to 0, because 21 is divided by 7 is 3 with a remainder of zeros, the remainder. Okay? So what do I have right now? So now I know that f of x, remember 2 was a 0, which we kind of knew it was going to be from my plug and chuck method here. So if 2 is a 0, then the factor, we'll clean it up later, is x minus 2. So my function is going to be x minus 2 times the quotient, the rest of it. This is the 2, 4, 2. This is constant x squared. It'll be times 2x squared plus 4x plus 2. So I factored it. But is it a factored of completely irreducible polynomials? Well, I don't know. Well, actually, I know it's not, because 6 was also a 0. So once you divide into it one time, take 6 and divide into the quotient from the other part. So here we go. I'm going to take 6 and divide it into 2, 4, 2. As in terms of synthetic division. Bring down the 2. 6 times 2 is going to be 12. Add, you end up getting 16. 6 times 16, time for calculator now. 6 times 16 is 96. And plus 2 is 98. But this is your remainder here. You want to sit there and put him back in the wonderful world of Z7 adjoint X. So 2 is good. 16 in terms of Z7, well, the 2 times 7 is 14. You get to 16, there's 2 left over. And then 98. And I'll just prove it to you. Here it is. 98 divided by 7 is 14. Even with no remainder. So the remainder is 0. So this tells me now the x equals 6 is a 0 because I got a 0 for the remainder, so the factor was x minus 6. So f of x is going to be that first factor, which was x minus 2, times the second factor of x minus 6, times what's left. This is your constant x term. You end up getting 2x plus 2. Now, little subtleties. This is the right answer, but you got a problem. Your problem is it's not completely right. We want to put it back in Z7 adjoint X. Z7, the coefficients have to come from Z7. 0 through 6, and they're positive. There's no minus on this. I want the equivalent positive equivalence class. So the actual answer, and there are going to be 2 of them we would accept, but here it is. The answer is that f of x would be equal to, instead of x plus 2, you don't want a minus, x minus 2. You don't want a minus 2. You want to add 7. That'll be an x plus 5. That's its equivalent term with a positive Z7 value here. And the next one is going to be times x minus 6. Well, minus 6 is not allowed. You want to put it into a Z7 element. So add 7 to the minus 6, you get 1. It gives you x plus 1. And then you got the other factor, which is just 2x plus 2. And this is fine. Remember, we talked about this last time. Factoring out a constant out of a polynomial is not really changing the polynomial. This is its associate. I do have a common factor that I can pull out of this guy. I could have pulled out the 2, and that would have been an or. And I would write my answer like this. I can factor out the 2, and I'll put him out front. It'll be times x plus 5 times x plus 1. And factoring out the 2, you get another x plus 1. And there's 2 different ways we could have written this answer, and we'll count them right either way. But I like to pull out the constant when I have one. The other thing you should notice is this. X plus 1 is a double root. It's x plus 1 squared times x plus 5 times 2. That's what this original polynomial was. So there's 2 different ways, and you factor it as a product of irreducibles. Because once you get to the linear factor, you can't factor a linear factor anymore except pulling out constants. But pulling out constants don't matter. It doesn't change anything. So let's give you another example here. Here I want you to factor as a product of irreducible polynomials. G of x is equal to x cubed plus 6x plus 5. And again, we don't typically put the little pointy brackets on there, but you'll notice my polynomial in standard operating procedure. Dr. Hungerford does occasionally violate his own rules and put some minuses in there, and that's okay, but officially you're supposed to make all these guys plus. And it's real easy. Just when you got a minus, add your mod number to it until the point where it becomes a positive number, because they're going to be equivalent. So what I'm looking for, the ability to factor a polynomial as a product of irreducible polynomials. I first look at my field, which is Z7 adjoint X once again, and I'm going to test the orders in terms of my congruence class. Okay, congruence class is a Z7 or 0, 1, 2, 3, 4, 5, and the last one is 6. And what we're going to do here is, just for time's sake, we're going to plug these numbers into my G function. And I'm looking for, after the correct modulo aspect of it, which one's going to end up being 0. So plugging in 0, I can do that. That's 5. But after that, you start getting hairy. I can plug in 1 too, but let's just do this. Y equals, clear out the whole function. This one's going to be x cubed plus 6x. Oops, let me do it again. X cubed over arrow plus 6x and then plus 5. So this is my polynomial, and I'm going to hit enter, and I'm going to do a zoom 6 on it, negative 10 by 10 screen. I don't care where the graph goes. I'm just going to do this. Second, calculate, find the value. First one is 0, and it should be giving me a 5, which it does. The next one, I plug in 1, I get 12. Plug in 2, and I end up getting 25. When I plug in 3, I end up getting 50. When I plug in 4, I end up getting 93. Plugging in 5, I end up getting 160. And plugging in 6, I end up getting 257. But we have to convert these numbers back so we can see what's going on to Z7 there. Adjoint X. So it's the Z7 we want. So 5 is good. And it's not a 0. 12, subtract 7, you end up getting, let's see here, 12 minus 7, which is 5 again. Just want to double check myself here. 25. 25 and multiples of 7 to not going over of 25 would be like 21. And 25 minus 21 is 4. 50, let's see here. In terms of 7 times 7 is 49. So 49, we're going to get 50 with 1 left over as remainder. So the remainder is 1, so that'll be it. 50 is equivalent to 1 in Z7. I have here, let's see what it was. When I plug in 4, I end up getting 93. This is a 93. So I can take, just to show you the other trick here, I can take my numbers 93, divide by 7. Let's see what the remainder is. So get rid of the actual 13 part, the whole part, and just take the fraction and see what fraction it is. It's 2 out of 7, so the equivalence class is going to be 2. 160 divided by 7. Subtract off the whole part of 22, and that gives you, converting it over to a fraction, 6/7. So the equivalence class would be the numerator, the 6th part. And the last one is 257. 257 divided by 7 is 36 point something or other. Subtract off the whole part, 36, and then convert the fraction part into a decimal fraction, and you end up getting 5/7. So the equivalence class is 5. Which one has equivalence class 0? There are no zeros. With no zeros, got to be equal to 0 for your root. That means if there's no zeros, there's no roots, because this is cubic. Remember our theorem about if it's degree 2 or degree 3, this will always work. There are no roots, which means that the polynomial g of x equals x cubed plus 6x plus 5 is irreducible in Z7 adjoint x. So this is how I can prove that it is irreducible. If I've got a polynomial that's either degree 2 or degree 3, and there are no zeros, roots to it, automatically it's irreducible. But once you get into the degree 4, degree 5, that's when you're going to be able to factor over other factors than just like what we're looking for, the linear terms and stuff. So, one more example. Put one similar to this one kind of on your homework that'll be due. Let's take a look at this guy. This one says this. Factor as a product of irreducible polynomials in Z5. I change it up on you. Z5 adjoint x And here it is. F of x equals x to the fourth plus 3x cubed plus 2x plus 1. Notice there's a term missing in here. Now, this one is x to the fourth. So, again, factoring this guy, if I don't find any factors, any zeros, this thing could still factor, but that's going to be a pain to try to figure out what that is. But let's look for the zeros first. Let's see if the zero game is going to work. But again, this is z5 adjoined x. So with that, we're going to be checking f of the equivalence class 95, a little bit easier. 0, 1, 2, 3, and 4. So I'm going to plug these numbers, 1, 2, 3, and 4, into my polynomial. Now, I know people are already wanting to talk to me, hey, there's an easier way using the table button. Yeah, I know about the table button here. I'm going to show you how to do that too. So I'm going to go to y equals, clear out the old graph, and type in the new graph. The new graph is this x to the fourth, over arrow, plus 3x cubed, over arrow, plus 2x, plus 1. And again, I can do the graph thing, or now I can go to my table setup. I want to start the thing at 0, and all I care about is 0 through 4. And then I go second table, and it tells me what my values are straight up. Y of 1, the y coordinate when I plug in 0 is going to be 1. So I can slide this over and just copy my numbers down. F of 0 is 1. F of 1 is 7. F of 2 is 45. F of 3 is 169. F of 4 is 457. But again, to analyze these guys, I got to pay attention to that field. That's why it's so important. It's Z5 adjoined x, so we've got to convert these guys into Z5 numbers. Well, luckily 5 is easy to divide by and figure out what the remainder is, so pretty much 1 is equal to 1. But 7 in Z5 would be equivalent to 2. 45 in Z5 is equivalent to 0 because 5 divides into 45. 169 will reduce to, let's see here, 169, well, goes into 165. Divide by 5 is either going to be 0 or 5, so I got 4 left over. And 457, well, it goes into a 455 times, so there will be 2 leftovers. And notice, boom, I got some victory here. I found myself a 0, 2. So x equals 2 is my 0 or my root, whatever you want to call that. I'll take it either way. So I'm going to do synthetic on that too. I'm going to divide it into the coefficients of my polynomial. But remember, if there's a term missing, you've got to put 0 in for it. So it'll be 1x to the fourth plus 3x cubed plus 0x squared plus 2x plus 1. Skip a line, draw a line. Bring down my first guy, 1. 2 times 1 is 2. Add 3 plus 2 is 5. Multiply 2 times 5 is 10. Plus 0 is still 10. 2 times 10 is 20. Plus 2 is 22. Multiply 2 times 22 is 44. Plus 1 is 45. But to figure out your polynomial, you've got to pay attention to it and convert it back into the wonderful world of that Z5 adjoined x. So in terms of Z5, 1 is 1. 5 is equivalent to 0. 10 is equivalent to 0. But 22 would be equivalent to 2. And the remainder, 45, well, 5 goes into 45 with no remainder, so it's 0. That tells me right there, and just writing in terms, if C is 2, x minus c is going to be the factor. It'll be x minus 2. I'll clean them up at the end, so you can just leave them like this for a second. X minus 2 times, this is your quotient over here. It is constant x, x squared, x cubed. It'll be times x cubed plus 2. Now, are we done reducing this guy? I don't know. Because I could have double roots. So, but if I'm going to have any other factors, the factors that come from this x cubed plus 2. So I'm going to call that guy a different function. G of x is equal to x cubed plus 2. And then I'm going to double check them again. I can check, this is in Z5, so 0, 1, 2, 3, and 4. But I can tell you honestly, all I really need is to check one of them. The one that I need to check is going to be 2. Because if it's a 0 now, it would have been a 0 before. And there was only one 0 before. So I really don't have to check these other guys, but I will prove it to you, so I will. But the only one that has a potential is going to be a double root. That 2 may show up as a 0 again. So let's just plug the numbers in. I think we can handle this without a calculator. Plugging in 0 to x cubed plus 2. 0 cubed plus 2 is 2. 1 cubed, which is 1 plus 2 is 3. 2 cubed is 8 plus 2 is 10. 3 cubed is 27 plus 2 is going to be 29. And 4 cubed is 64, if I remember correctly. Yep, it's 64. Plus 2 makes it 66. But again, converting them back into the wonderful world of Z5, adjoint x. These numbers end up becoming 2 is equivalent to 2. 3 is equivalent to 3. 10 is, in terms of Z5, will end up being 0 because 5 divides into 10 with no remainder. 29, you can keep subtracting factors of 9 out of, but 29, keep subtracting by 5s if you want to, or just divide by 5 and it's the remainder. Well, 25 goes into 25 5 times with 4 left over for the 29, so 29 is equivalent to 4, and 66 would be equivalent to 1 because 5 goes into 65 with 1 left over. But notice, boom, 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 I got another 0. So my factor again of these g functions are going to be x equals 2. So I'm going to divide 2 into my coefficients of x cubed plus 2. So this will be 1x cubed, no x squared, so I'll put the x cubed up there, x squared, x, and constant. So it's 1x cubed plus no x squared plus no x plus 2. Skip a line, draw a line. Bring down your victim, 1. 2 times 1 is 2, put it up here. And 0 plus 2 is 2. 2 times 2 is 4. 0 plus 4 is 4. 2 times 4 is 8. Plus 2 is 10. But you have to go back and convert it back into the wonderful world of Z5 or whatever field you're playing with. So 1 is good, 2 is good in Z5, 4 is good in Z5, but 10 is equivalent to 0. So now, boom, 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 I get another factor of x minus 2, and my divisor is going to be x squared, x, and constant here. So this will be 2x squared plus, x squared, put my 2 in the wrong spot, x squared plus 2x plus 4. So now I keep factoring that polynomial. It'll be x minus 2 from that first division that we did. I got another x minus 2 because this was a double root, and then I got the rest of it, which is the now reduces down to x squared plus 2x plus 4. Now, are there any other zeros in this thing? Well, I got to now check it on this guy. So I'm going to let h of x be equal to, because these guys are linear. Once you're done linear, you're done with finding zeros. So if any other zeros, they've got to be in the x squared plus 2x plus 4. But if, and again, I'm going to check the numbers 0, 1, 2, 3, and 4. Again, I'm just being consistent on here, but honestly, 0 wasn't a 0 in the beginning, 1 wasn't a 0, 3 wasn't a 0, and 4 wasn't a 0. It wasn't the first time, it wasn't the second time, it's not going to be the third time. is this guy going to be a triple root or not? Well, let's find out. So all I really need to do is actually plug in 2 again, but I'll plug in all these numbers into this guy. Plugging in 0, I get 4. Plugging in 1 plus 2 is 3, plus 4 is 7. Plugging in 2 squared is 4. 2 times 2 is 4, 4 plus 4 is 8, and 8 plus 4 is 12. Three squared is 9, plus 2 times 3 is 6, plus 4 is 19, and 4 squared is 16, plus 2 times 4 is 8, plus 4 is 28. But again, putting this back into Z5, 4 is 4, 7 is 2, 12 is 2, so 2 is no longer a 0 anymore, so I'm pretty much done, but the rest I'm going to show you. 19 is 4 in Z5, and 28 is 3 in Z5. No more zeros, which means I am done factoring it, but one last move. We want to be in Z5 adjoined X as a polynomial factored into irreducible polynomials. And officially, I'm not allowed to have this -2 of an equivalence class, so this is in Z5, so I just got to convert -2 into what is equivalent between 0 and 5. So -2, add 5 to it, gives me +3. So this will be X plus 3. -2 is equivalent to +3, so it'll be times X plus 3, your double root, and then you got the rest of your polynomial X squared plus 2X plus 4. Now it is a factor of irreducible polynomials. We've reduced f of x to a product of irreducible polynomials. So you got to check for those darn double roots and the like, and making sure that there are no more roots. But notice the technique, and it goes right back from high school, called the remainder theorem and the factor theorem. So there you go. Well, I hope this has been helpful. I'll see you on the next video.